So continuing on talking about logarithmic and exponential equations, now that we've talked about the functions, let's recall that y equals the log base a of x if and only if it's true that a to the power of y equals x. So those two things are equivalent. On the right, we have exponential form, and on the left, we have logarithmic form. And then we have some properties of logarithms that said if you have a log of a product, you can write it as the log of the first factor plus the log of the second factor, and those will be equivalent. You will get the same result either way. And then if you have the log of a quotient, you can write that as the log of the numerator minus the log of the denominator. And then we have this really useful property that says if our argument of our logarithm has an exponent on it, the exponent can come out in the front and become a multiplier of the logarithm. And then we also have this property that a to the r can be rewritten as e to the ln of a to the r, because e to the power of and ln of undo each other. They're inverse functions. And then this r can come out in the front to give us e to the r ln a. And this is a really handy tool for using in calculus. So let's solve logarithmic equations. And the first type we're going to solve are pretty basic. And if you can manipulate your equation until you have one logarithm on each side with no multipliers, then you can use this property that says if two logarithms are equal, then their arguments have to be equal. So we use the properties of logarithms to take care of this multiplier of 3 and write it as log base 2 of x cubed. So we use the property the other way of bring the multiplier up as an exponent. And then that has to equal the log base 2 of 27 to the power of negative 1. So now that we have two logarithms that are equal to each other, it has to be true that their arguments are equal to each other. And so x cubed has to equal 27 to the negative 1. So let me write that as x cubed equals 1 over 27. And then hopefully you see that by doing the cube root of both sides, we get x equals 1/3. So the x that works in this equation is x equals 1/3. Okay, then the second example here is really similar, where we're going to say, let me take this log base 5 with 2 multiplying in the front and bring the 2 up as an exponent instead. And then I'm going to have the log base 5 of the 4, and that's going to be to the power of the 3 that I bring up as an exponent. So if two logarithms are equal, their arguments have to be equal. So we have x squared equals 64. So the solution to this equation is x equals plus or minus 8. So don't neglect that minus, but then you should go back to the original problem and say, well, I have an x in argument of a logarithm, so x has to be positive because of domain of log function. So we know our only actual answer is going to be x equals 8. Okay, so when you're solving more complex logarithmic equations, you will first want to combine all the logarithms into a single logarithm using your properties of logs, and then write the equation in exponential form. So those are the steps. Get all the logarithms into one log and then write in exponential form. So let's look at this first example where we have one log minus another log. So we know that means you can write this as the log of the quotient of the two arguments, and that has to equal 1. So I've combined the logs into a single logarithm, and now we're not seeing a base. This is the common log that has base 10 that doesn't get written. It's understood to be a 10. So then I write in exponential form as 10 to the 1 equals 2x over x minus 3. And we can solve this. So whenever the variable you're trying to solve for is in a denominator, multiply both sides by the denominator so that you don't have a denominator anymore. So then you're going to have 10x minus 30 equals 2x, because these guys are going to cancel. And then you do some algebra, subtract 2x and add 30 to get 8x equals 30. Divide both sides by 8 and get x equals 15/4. And then we should check and make sure 15/4 works. And one way to do this is to, at the beginning, say, well, I can see x has to be greater than 0 and x has to be greater than 3. And 15/4 is greater than 3. So you can either find the domain of the function in the equation and then verify that 15/4 is greater than 3, so we're okay. Or you can plug the 15/4 back into the equation and say, well, I'll have the log of 2 times 15/4, that's fine, minus the log of 15/4 minus 3, and that's fine. So do make sure that you check, though. You can't just ignore the check step. Sometimes there's only one answer that works. Sometimes there's no answer that works. So don't neglect that check step. Okay, so B is got logarithms on each side. So I'm going to add log base 5 of x minus 1 to both sides so that I'll have both of the logarithms on one side. So then I'm going to have log base 5 of x plus 3 plus log base 5 of x minus 1, and that equals 1. So then I'm going to combine my logs into a single log using that product property. So I'm going to have as a product inside my logarithm x plus 3 times x minus 1, and that has to equal 1. So now that I have a single logarithm, my strategy is to write in exponential form. So I'm going to have 5 to the 1 equals x plus 3 times x minus 1. So this is going to be quadratic, so I need to get x squared plus 2x minus 3 on this side and the 5 on the other, and then I need to get 0 on one side to solve a quadratic. So then we're going to factor, get 0 equals x plus 4x minus 2. And then we use our 0 product property and say, well, that means either x plus 4 is 0 or x minus 2 is 0. So that's going to give us two possibilities. X is -4 or x is 2. We have to check. So let's first check x equals -4. Well, we would have the log base 5 of -4 plus 3. Well, you can stop right there because you can't take log of a negative number. So you can write as little as that. You can't take log of a negative. So x equals 4 is not a solution. So x can't be -4. So then let's check x equals 2. And we have the log base 5 of 2 plus 3. And we want to know if that equals 1 minus the log base 5 of 2 minus 1. Well, that looks like it works just fine to me. We have log base 5 of 5 equals 1, and the log in any base of 1 equals 0, and the log base 5 of 5 is 1. So x equals 2 is your only solution. Okay, so the next one has more steps to it, but the idea is the same. Oh, actually this one, the idea is a little bit different. Have logs on both sides. So why not just try and get one log on each side and have this red box set up where I have a log on each side. So let's see, I'm going to take this 2 and bring it up here as an exponent. So I'm going to have the log base 3 of x minus the log base 3 of 5 squared. And that's going to equal the log base 3 of x plus 1. I'm going to bring this 2 up as an exponent minus log base 3 of 10 squared. So now I'm going to use my properties of logarithms, and I'm going to have the log base 3 of x over 25 equals the log base 3 of x plus 1 over 100. So now I know that it has to be true that the arguments are equal. So I can write that math equation that says x over 25 equals x plus 1 over 100, because the arguments must be equal. And then I want to solve for that x, so let's multiply both sides by 100 so I don't have fractions. So I'm going to have 4x equals x plus 1, subtract x and get 3x equals 1. X equals 1/3, and then just at least come back up here and check and say 1/3 is fine here, 1/3 is okay here, so that is our actual solution. Okay, so then this D example, this is a little different example. So let me let you look at it for a moment and think about that. Boy, it has a really different look to it than these others, where it has a square root of a logarithm. So this is thrown into the logarithm section, and it's another example of quadratic in form. So are you seeing that if we let w equal the square root of the ln of x, then w squared equals ln of x, and I can rewrite my equation as w squared minus 3w plus 2 equals 0. So then this is not too bad to solve. We'll have w minus 2 and w minus 1. So then I use my zero product property. Say either w minus 2 is 0 or w minus 1 is 0. So that gives me two possibilities. Either w is 2 or w is 1. So let's go back to our equation and check w equals 2. So I'll have 2 equals square root of the ln of x. That would be w equals 2. So squaring both sides, I'm going to get 4 equals ln of x. And then remember there's a little base e here that we're not seeing. So to solve for x, we're going to get x equals e to the fourth. So then we can see that our domain is just positive values of x. And e to the fourth is always positive. So here is one of our solutions. And then let's see what happens when w equals 1. So I'll have 1 equals the square root of the ln of x. Square both sides. And get 1 equals the ln of x. And again, there's a little base e, so e to the 1 equals x. And that's also positive, so x equals e is also a solution. So e and e to the fourth. Those are our two solutions. Okay, so I'm going to pause here and then we'll come back and do exponential equations.